Welcome. This podcast is on looking at how materials are characterized by their chemical bonding. We're going to be exploring four different types of bonds and looking at, for this learning target, how bonds affect the property of the material. So, bonding occurs to make atoms more stable. It allows atoms to achieve a full valence electron shell. In other words, remember valence electrons were the outermost electrons, the ones that were in the outermost orbital of a Bohr model. And so we're going to look at how ionic, covalent, network covalent, and metallic bonds form and the properties of the materials associated with the bond type. So an ionic bond forms between oppositely charged particles, ions, due to an electrostatic attraction. Metals, any of our metals on the periodic table, when they bond with nonmetals, bond in an ionic manner. And what we mean by that is they form ions because the metal gives away its electron, fully transfers it to the nonmetal, and so the metal becomes an ion with a positive charge, a cation, whereas the nonmetal becomes an ion with a negative charge since it's gained electrons, the anion. Ionically bonded substances have a crystalline structure, extremely high melting points. They're very brittle, and they conduct electricity as a solution, but not as a solid. So we'll be looking at why those properties are what they are, but much of that is based on the bond type and the strength of the attraction between the atoms. I would remind you that it's super important to draw in molecular view images. So take a second in your notes and draw in the sodium chloride ionic bond that you see here on the screen. Covalent bonding is the sharing of electrons between nonmetals, both that have a really high electronegativity. So if we look over here on the periodic table, we can see that metals are a much smaller area on the periodic table. They have similar properties and similar electronegativity values. Neither nonmetal is powerful enough to steal the electron from the other atom. And so instead of stealing it and transferring it like an ionic bond, it has to share it, which is a covalent bond. Because they're sharing electrons, there's a different strength holding the atoms together. And so covalently bonded substances tend to be insulators and resistant to corrosion and can be either soluble or insoluble in water. Here's pictures, and I would encourage you to draw the molecular view images of two covalently bonded substances, one of which is nonpolar and the other is polar. So a nonpolar covalent bond is two different atoms that have such similar electronegativity values or symmetry of the atoms that the electrons are shared equally. Thus, there's no partially positive or partially negative charges. There's no charges at all. And so nonpolar covalent substances will have a different solubility than polar covalent substances because of that. So if we look, this chlorine atom is sharing an electron with this chlorine atom, which is sharing an electron, but those electrons are being shared equally between the two atoms. That's what makes it nonpolar. A polar covalent bond is when the electrons are being shared, but not equally. This is the equivalent of if you're the older sibling and you say, oh, I'll split the last piece of cake with you to your younger sibling, but you take 70% of it and give them about 30%. Yeah, you shared, but not equally. Since it's not equal in how it's being shared, we develop a partial positive and a partial negative charge. In other words, chlorine is the bigger winner of this electron. This electron is situated around chlorine, giving it a partial negative charge more than hydrogen, which is why hydrogen is partially positive. Again, if something is polar or nonpolar, it affects solubility. So a network covalent bond is a chemical compound or elements in which atoms are bonded through covalent bonds, so these must be nonmetals, in a continuous network extending throughout the material. Properties of network covalently bonded substances are extremely hard and have extremely high melting points due to the strong covalent bonds throughout the lattice. So, diamond and graphite are an example of a network covalent bonded substance. Both are made of pure carbon, but they come together in very different crystal structures with different lattices, which give them very different properties. And network covalent bonds allow for the formation of allotropes. An allotrope is the same element, but with a different crystal structure and properties, such as color and hardness. We're going to have some really cool labs coming up where we look at allotropes and changing the crystal structure of something without changing its composition, which will allow the properties to change. An example of allotropes are O2 and O3. They're both oxygen, but oxygen, O2, that we breathe in the air, is very different than ozone, O3, which is considered hazardous and a source of pollution. Diamond or graphite, as we discussed on the previous slide, or red and white phosphorus. We're going to watch a quick video that examines white and red phosphorus and its properties.
Phosphorus can exist in several different forms, which are known as allotropes. Unlike other elements, phosphorus doesn't like to exist as free atoms, so it makes different structures, and depending on which structure it makes with itself, you get the different types of phosphorus. The photos I have for the structures of phosphorus aren't the greatest, but I hope from them you can see that there is a difference. The common forms are white and red, and violet and black phosphorus are much rarer. In this video, we're focusing on the white allotrope, and it's really the most dangerous of them all. Most of the other ones are pretty stable under air, and they're not very toxic actually. Whereas white phosphorus is quite toxic and ignites spontaneously under air. The big thing that white phosphorus does to you if you're exposed a lot to it is it gives you something called phossy jaw. The white phosphorus accumulates in your jaw, and as you'll see later in this video, white phosphorus glows in the dark. So if you get enough, your jaw could actually glow. While that can be cool, it also causes necrosis of the jaw and the surrounding tissue, which is less fun. The major controversial use of white phosphorus, which gets it into the news sometimes, is its use as an incendiary weapon. First, I get a sample of white phosphorus, which is safely stored under a little bit of water. And then to remove a small piece, I use my knife. When I start to cut it, it looks like it's soft, but suddenly it cracks and pieces fly everywhere. From all of the shattered pieces of phosphorus, you can see white fumes of phosphorus pentoxide coming off. The phosphorus pentoxide forms when the white phosphorus reacts with oxygen in the air. Phosphorus pentoxide itself is dangerous because when it comes into contact with water, it forms phosphoric acid. Normally, when white phosphorus is exposed to light, it actually becomes a yellow color. It's pretty easy to see that my white phosphorus is actually reddish orange and not yellow. I assume my white phosphorus is discolored like this because it's extremely old. Anyway, now for the fun part of lighting it on fire. Using a barbecue lighter, I light it on fire and you can see that it quickly gets going. To put it out, I simply place another crystallizing dish on top to cut out its oxygen supply. And now to show you the scary part of white phosphorus. You see, right when the crystallizing dish is removed, immediately it starts burning again. This is because it can spontaneously ignite at temperatures as low as 30 degrees Celsius. So you can imagine how hard it is to extinguish any white phosphorus if you ever were to get any on you. To extinguish it, I'd put a little bit of water in, so when the crystallizing dish is removed, it will immediately be covered. So you can see that it's successful, and when it's removed, there's no burning white phosphorus. And now I pour out the water to expose the wet white phosphorus below. You can see that immediately when it's not under water, it starts to fume again. This is from a second run, but you can see that just after several minutes of sitting out, it's fuming a lot. and eventually it will heat up enough to spontaneously ignite itself. So you can see what makes white phosphorus so scary. If you get it on you, you can't just extinguish it, you actually have to completely get rid of it. And then also, as I mentioned earlier, the phosphorus is poisonous, so even when it's extinguished, it's still going to be leaching into your body. I apologize for this shot being a little unfocused, but the point of it is still pretty clear. When the phosphorus burns, it lets off a lot of smoke, which makes sense why it's often used to make smoke screens. This is just to show that it can be a little hard to put out the phosphorus, and you see that I spray it with a little bit of water from the hose, and it causes burning phosphorus to splash everywhere. If the fire was much larger and there was a lot more phosphorus, you can see how spraying it like that could actually just spread it more. As a final test, I place a small amount of white phosphorus on a piece of meat, and then just like before, we light it on fire and let it burn. And then to extinguish it, I put a crystallizing dish on top, just like before. And then I take it away to see that again, just like when it was on the glass, it reignites. I let it burn for a while, but it was producing a lot of smoke, and I was worried that somebody would call the police. I extinguished the phosphorus and removed it, and there was still a lot left that hadn't burned. The white phosphorus burned for about a minute, and it burned away about a fifth of the thickness of the meat. I don't show it here, but the underside of the pork, even after a minute, was still uncooked. I don't have any real conclusions to draw from this experiment, but I was honestly surprised because I thought the white phosphorus was going to do a lot more damage. And this is just a final demonstration to show how white phosphorus exhibits chemiluminescence. When exposed to moist air, the white phosphorus is oxidized and it lets off a very faint green glow. In person, it's actually pretty distinct, but on camera, it was very hard to pick up. So that about wraps up everything I had to show about white phosphorus. Fortunately, I didn't have any carbon disulfide that I could use to show the solubility of the white phosphorus, but if there's anything else that I missed or that you'd like to see, leave a comment below.
All right, so the last bond type we'll explore is metallic bonding. Metallic bonding is formed from the attraction between mobile electrons and fixed positively charged metallic atoms. So if we look at our picture over here, which again I would encourage you to draw, we have the positively charged metallic atoms that are in fixed positions, and the electrons are mobile and can move anywhere within this structure. So, since the valence electrons are very loosely held, they're a free moving sea of electrons. This allows metals to be excellent conductors of heat and electricity and allows them to reflect light, be malleable, and be ductile. So, a metallic bond between two different metals, a metallic bond between a single metal would just be a pure metal, but a metallic bond between two different metals would form an alloy, which is a mixture, not a compound. If you remember back to our first learning target lesson at the beginning of the year, it would be a mixture because we can put it together in any ratio, whereas compounds require very specific ratios to form in. For example, aluminum oxide forms with two aluminum atoms for three oxygen atoms, whereas a mixture of something like brass is an alloy because it's a mixture of two different metals, copper and zinc, in any ratio. So we'll watch a quick animation of a metallic bond to see the movement of the electrons. As we can see, the atoms in the metal are arranged in a regular manner and vibrate in fixed positions. It's the outermost valence electrons that are moving freely, forming that sea of electrons. And thus, the sea of electrons is holding the atoms together. This is why it's metallically bonded. Generally, they move in random directions, but when we apply a current, a positive and a negative potential difference, we can get them to move in a specific direction, which would be an electrical current. So, to summarize, I would highly encourage you to make this chart into your notes. You have this on your workbook, but if you don't have your workbook with you, let's replicate this chart in your notes. And whether you use your notes or in your workbook, let's make sure we completely fill this in. It's a great reference for the remainder of the year. When we're talking about types of bonding, the type of element in a metallic bond would be only metals. That means it would be only cations or the elements on the periodic table that give away their electrons. It would be a sea of mobile valence electrons in terms of the arrangement of electrons within the bond. And so this would be pure metals, elements, or alloys, mixtures of multiple metals. The bond strength is relatively strong, and that means that metals are good conductors, workable, and corrode easily. Ionic bonds are metals and nonmetals. That means that it's a cation and an anion. The cations give away their electrons to the anions, so there's the complete transfer of valence electrons from one to the other. Thus, the types of materials this occurs in are glass and ceramics, and the bond strength is very strong because of this. That gives them very different properties. They're brittle with very high melting temperatures that do not corrode. Covalent bonds are formed between nonmetals only. That means that it's anions. And because they have very similar electronegativities, the electrons are not transferred, they're shared. If they're shared equally, it's a nonpolar. Unequally, it's a polar covalent bond. This occurs in polymers and proteins, and the bond strength is very strong. But covalently bonded substances are insulators. They don't corrode. And finally, we didn't talk about it in this podcast, it's coming on a different day, but intermolecular forces, hydrogen bonds, form between nonmetals. The bonds are anions. It's an unequal sharing of electrons. This is the type of bond that occurs when a polymer is cross-linked. It's a pretty weak bond compared to the others, and this determines the properties of plastics. So let's just practice. You should already have a color-coded periodic table with your red, yellow, and blue parts. Red being metals, yellow metalloids or semimetals, and blue nonmetals. If I ask you what type of bond would form with magnesium, well, magnesium's right here in the red section. So if there's only a metal involved in the bond, this must be a metallic bond because metallic bonds form with only metals. In this case, it's not an alloy, it's a pure metal because it's just elemental magnesium. What about sodium chloride? What type of bond forms with sodium chloride? If you looked on the periodic table, sodium is a metal, chlorine is a nonmetal. Metal with nonmetal. Yep, it should be an ionic bond. Ionic bonds form between metals and nonmetals. All right, try it yourself. How about CH4? Hopefully you told me that was a covalent bond because carbon is a nonmetal and hydrogen is a nonmetal. So if we have only nonmetals in the bond, it should be covalent. SO2? Again, I hope you told me this was a covalent bond. Both sulfur and oxygen are nonmetals, and so if only nonmetals are involved, it's a covalent bond. Cu, copper. That's a metallic bond because copper is a metal, and if we only have metals, it must be a metallic bond. In this case, it's a pure metal. And if I told you there was sharing between electrons, what bond type would that signify? Hopefully, you looked back in your notes and recognized that that would be covalent because covalent bonds or nonmetals have similar electronegativities. The electron isn't transferred like an ionic bond, it's shared. And so that happens with a covalent bond. I hope this was helpful. Thanks for watching.